Okay, so I forgot to hit the record button while I was in class. So here, what I'm going to do is, I guess I'll just re-record it. So anyway, let me pull up the questions here and then we can get started. Okay, so first question, 1A. This is, okay, again, I should write, which of the following are injective / surjective? Okay, for bijections, write the inverse. Okay. I guess I should write a little bigger so people can see. Anyway, so the first question here, we have our function f with domain, the real numbers, and codomain, once again, the real numbers. And the function is given by f of x is equal to the absolute value of x. Question is this injective and or surjective? Well, it's not injective because if you recall, the definition of injectivity is that f of x1 is equal to f of x2 implies that x1 equals x2, okay? And this is true for all x1 and x2 within our domain. Here, that's the real numbers. But the issue here, note, is that we have f of 1 is equal to f of minus 1, right? Because they're both equal to 1. And 1 is not equal to minus 1. Okay? So we do not have this implication. So f is not injective. Just like that. What about surjectivity? Well, remember the definition of surjectivity is that there exists a y in the codomain, which is our real numbers, such that, there exists a y in the real, okay, I'll just cut this one out. Okay. So for surjectivity, the definition is that for all y in the real numbers, there exists an x in our domain, which is, again, the real numbers, such that f of x is equal to y. Now, is this true for all y in our codomain? Well, the answer is no, because if I take y is equal to minus 10, let's say, right, then there does not exist an x in R such that f of x is equal to minus 10. Why is that? Well, let's draw a picture of our absolute value function here, right? This will be our absolute value function. You note that there are no negative values in the image of the function, right? It does not hit any of these negative y values. So it's not surjective. Not surjective. Okay. Moving on. B. Okay. We have f from the real numbers to the codomain, which is all numbers between 0 and 1 inclusive, and 2. And our function here is given by f of x is equal to the sine of x. Is this an injective function? Well, let's see here. I let f of x1 equal f of x2, which means just by definition that sine of x 1 is equal to sine of x2. Now the question is, okay, so this is, don't write this down, but the question is, does sine x1 equal sine x2? Does that imply x1 is equal to x2, right? There's a question mark there. Well, it doesn't. Why? Because, okay, no. Why? Because f of, let's see, 0, okay, is equal to f of 2 pi, right? Which both have values 0. You take the sine of 0 and 2 pi, you get 0. And 0 is not equal to 2 pi. So f is not an injection. The question is f a surjection? Well, note that when I take the sine of any number, I always get a value that's between -1 and 1, right? I will never get a value that's greater than 1, so I cannot get 2, okay? So I guess since 1 is less than or equal to sine x is less than or equal to 1, is -1, and for all x in the real numbers, it means that 2 is not an element of the image of f. So, not surjective either. Right, and there you have it. Okay, moving on. Here, let's see. We have C now. F from the real numbers to the codomain, which is interval 0, 1, all numbers within 0, 1, and f of x equals the sine of x again. So once again, question is this an injection? Well, once again, it's the same thing as before, right? F of 0 is equal to f of 2 pi which is equal to 0. Okay. Then essentially 0 is not equal to 2 pi, once again, so it's not injective. Okay, by the way, I should mention, even in the solutions, there should be a -1. The previous question should also be a -1 to 1. Okay. Is it surjective, though? Well, the answer is yes. Okay, so let y be an element in -1 to 1, our codomain, right? The question is, does there exist x in R such that the sine of x is equal to y? Well, yes. The answer is yes, right? We solve for x, and we get x is equal to the sine inverse of y. And it's important to note that our x is an element of the domain, okay? That is very important to note. So it's surjective. There you have it. Okay, D. We have f defined from minus pi over 2 to pi over 2. Let's see, -1 and 1. Okay. Again, we have f of x is equal to sine of x. Is this a surjection or an injection? Well, let's see here. We let f of x1 equal to f of x2. What does that mean? It means that sine of x1 is equal to the sine of x2. Now, we can take the sine inverse of both sides And what that will give us is x1 is equal to x2. Okay? Now, we couldn't do this for the previous questions because our domain was not minus pi over 2 to pi over 2. It was the entire real numbers, right? So when you take the inverse, you can have more than one value given to you here. Essentially, if you want me to draw that, this is what this graph looks like. Okay, we have something like this. Okay, so minus pi over 2 to pi over 2. And then our graph in B looked a little something like this. Like that. Okay, now you notice that, if you apply the horizontal line test, it fails, right? It's not injective, but here, this function is only defined on this tiny interval here, and it is injective. That's why we can take the sine inverse and get the same values here, okay? Some people call it arcsine, okay, when we're dealing with this interval here. Right, so it's injective, okay? Now, is it surjective? Well, once again, we have something similar to the other question, right? Where we let x equal, sine of x equal y, then x equals the inverse of y, right? We can do that same thing here, right? Because we know this goes from -1 to 1, graphically speaking, right? So we can follow the same steps, and we can conclude that it is also surjective. Okay. Now, obviously, we've done this because we have a bit of foreknowledge of what the graph of sine actually looks like. But there are functions where you can't really draw it out and reason it out that way, right? Or use that to reason these out, right? It's not enough to draw a graph, okay? Don't do that. You will not get full marks for that. You have to do this. You may not get any marks for that. Okay, so let's take a look at one of those examples where it is easy to imagine, easy to draw, but we might not know it as well as the graph of sine of x. So let's see here. We have 1e now. Okay, so we have our function which goes from the real numbers to the real numbers, given by f of x is equal to, and now we've split it up into cases, okay? 0 if x equals 0, and 1 over x if x is not equal to 0, okay? Now, we want to check injectivity, okay? But the thing is, we have these two cases, okay, of x. So what do we want to check, okay? We want to check, first let's assume that f of x1 is equal to f of x2, okay? For some x1 and x2 in our domain values, okay? The issue here is that we want to know which of these cases x1 and x2 satisfies. Okay, so we have to break it up into cases here. So what is case 1? Case 1 is x1 equals 0 and x2 is not equal to 0. Okay, these are the two possible cases here. This is a 2. Then what happens? Then, well, let's see here. F of x1 is 0 and f of x2 is 1 over x2. But we know that this value cannot be 0. Okay? What does this mean? This means that f of x1 is not equal to f of x2. Okay, now if you were in class, I put check marks and x's here, so there might have been some confusion. But we've proved injectivity for this case here, okay? We've proved the contrapositive, right? So, if x1 is not equal to x2, then fx1 is not equal to f of x2, okay? It's just the contrapositive of your injectivity definition. So it satisfies injectivity in this case, okay? So make no mistake, okay? The function is injective in this case, okay? For these cases, I should say. What about case number 2? We could have x1 not equal to 0 and x2 equal to 0. Then we have f of x1 is equal to 1 over x1, which will never be 0. But we also have that f of x2 is equal to, well, 0. And again, we have that f of x1, okay, is not equal to f of x2, right? Here, x1 is not equal to x2, which implies f of x1 is not equal to f of x2. So for this case, the function is injective, okay? When x1 is not equal to x2, okay? When x1 is not equal to 0 and x2 is equal to 0. What are the remaining cases? Well, we could have x1 equal to 0 and x2 equal to 0 as well. But in this case, we have nothing to prove, okay? This is the conclusion that we wanted, that x1 equals x2, right? We assume f of x1 equals x2. We want to prove x1 equals x2. Well, in this case, they are already equal, so there's nothing more to do. So it's also injective in this case, okay? Or, you know, satisfies the definition of injectivity for this case. Finally, we have, what else? We could have x1 not equal to 0 and x2 not equal to 0. What happens in this case? Well, let's see here. We have f of x1. Remember, okay, this is what we were assuming, so I'm just going to write it here. F of x1 is equal to 1 over x1. But we assumed, remember, this is our assumption, that this is equal to f of x2, which is 1 over x2. Okay, so now we have this is equal to that. What does this mean? Well, let's just cross multiply, and you get x2 is equal to x1, right? Multiply this side by x2, multiply this side by x1, you know, multiply both sides, sorry. So it's injective in this case, or satisfies the condition of injectivity. So since, you know, injective in all cases, f is injective, okay? Great. What about surjectivity? Well, let's take, remember, to prove surjectivity, we have to take an element y in our codomain, which is the real numbers here. But again, we have this broken up into cases here, okay? X is equal to 0 and x is not equal to 0. So let's break this one up into cases as well. If y equals 0, then does there exist x in our domain range such that f of x equals 0? Can you find one? Well, yes, you can. Okay, f of 0. Yes, take x equals 0. Okay, what about if y is not equal to 0? What do we do then? Well, in order to find an x that satisfies f of x equals y, then we need, okay, what do we need? Well, f of x, it's not going to be 0, right? Because y is not 0. So x needs to not be 0, which means f of x is 1 over x equals y, which means that the x that we need is 1 over y. Okay? This is the value that'll give you f of x equals y. And so the important thing also is to note that x equals 0 is in our domain, and if you take 1 over y for any non-zero real number, you will also get a real number, non-zero real number. Right, this is also in our domain. So f is surjective. Okay? Great. Let's see here. Okay, now that means that since f is surjective and injective, f is bijective as well. Now we need to write the inverse. Well, we've already done most of the heavy lifting, right? You go back to how we found surjectivity. Then the inverse, right, f inverse, will be from, let's see here, the range, right, or sorry, this is the domain of the inverse, but this was the range of the function. But it turns out that they're both the same, so I guess it doesn't really matter. Right, to this, okay, defined by f of y is equal to 0 if y equals 0, and 1 over y if y is not equal to 0. Okay. Now you'll note that the inverse is actually the same as the function, right? These are called involutions. You might see them again. You might not. I don't know. Okay. Let's move on here. Okay, question 2. These are our counting questions, okay? These ones are not that long. So a four-digit pin is chosen using numbers, okay, 1 to 9. First question, okay, if chosen, okay, or selected, I guess, without replacement, how many pins are possible? Okay, well, let's see here. We have to choose, we have to select 4, right? And so, you know, suppose we have 4 options. And each time we're going to select from 9 possibilities. So the first time we do this, we have 9. And then for each of those options, we lose 1 option, right? Say I choose 1, then my next digit will be from 2 to 9 because I'm selecting without replacement. So there's 8 for this one, and then I lose 1 again, 7, and then 6 for each of those. And so total, I have 3,224 possibilities. Okay. B, let's see, if chosen with replacement, okay, if your pin number is chosen with replacement, how many are possible? Question mark. How many are possible? Well, again, let's see here. I have 4 options. I have 9 for the first one, and then for each of those, I have 9 again because I can repeat the numbers, okay? Because I'm selecting them with replacement, so I don't lose any, unlike the one in A. So times 9. So it turns out that that is equal to 6,561 possibilities. Okay. C. Where is it? Okay. Now suppose the order, okay, of numbers within the pin does not matter. Okay, so if 1, 2, 3, 4 is your password, then I consider that the same as 4, 3, 2, 1. Okay, the order does not matter. Question is, if selected with placement, with replacement, how many pins do you have? Okay. Well, we're saying that the order doesn't matter, and we're selecting without replacement. Well, this is just, by definition, going to be 9 options, and then we have to choose 4, okay? This is what it'll be, and this turns out to be 126, okay? If you don't know where this is from, I believe in one of your lecture notes, this is derived, right? This is what we use when the order of the selections does not matter, and we're selecting with, without replacement, okay? They should be without replacement. Yeah. Okay, so for D, okay, again, I'm going to, order does not matter here, okay? Suppose order does not matter. But this time we select with replacement. How many pins do we have? Okay. Well, let's see here. Okay, hang on. So we have, well, this is your classic n plus k minus 1, choose k, right? That's how many unordered subsets there are from a set of size n if you sample with replacement. So for this one, we have 9 plus 4 minus 1, 4, which works out to 12, choose 4, which is exactly 495 possibilities there. Okay, well that were the counting problems. Those were the counting problems. Okay, question 3. A. Let R be a relation on the power set, okay? You know, the power set of the natural numbers, right? So all possible subsets of the natural numbers, right? Where we say S1, right, a subset 1, or a set in the power set, is related to S2 if there exists a bijection F from S1 to S2. Okay? If you recall, what this is essentially saying is that, i.e., the size or the cardinality of S1 is equal to the cardinality of S2. But we're not going to use this definition, okay? If you use this definition, the problem becomes trivial. So we're going to use this one. Okay. So let's see here. To prove it to be we need to prove R is an equivalence relation and find all EQ classes. Okay. Well, let's see here. To prove R is an equivalence relation, we need to let S1, okay, just so we're clear with our notation, let those be an element of the power set. Now we need to prove that S1 is related to S1. Okay, we can do that if we can find a bijection from S1 to itself. And in fact, there is a bijection. F from S1 to S1 given by f of x is equal to x. You map it an element from S1 to itself. Okay, if you do that, then f is a bijection. Okay, and so S1 is indeed related to S1. Now, what about if S1 is related to S2, then we need to prove that S2 is related to S1. So if we're assuming S1 is related to S2, then let F be a bijection from S1 to S2. Okay? Then it turns out that we can take the inverse of f, and we know that an inverse exists because f is a bijection. Okay, so then f inverse, okay, from S2 to S1, right, you have to flip the domains and the codomains, is also a bijection. And this is a property of all bijections, okay? That the inverse of a bijection is also a bijection. Okay? So, what does that mean? Well, that means that S2 is related to S1. Okay? Now, what else do we want to prove? So that was reflexivity. Symmetry, we need transitivity, okay? Where if S1 is related to S2 and S2 is related to S3, then we want to prove that S1 is related to S3. Okay. Well, what does our assumptions give us? S1 related to S2, then we let, let's say G from S1 to S2 be bijective. Okay, bijective. And S2 related to S3 gives us a bijection. We know that there exists a bijection H from S2 to S3. Right, this is just our assumptions here, okay? S1 are 2 and S2 are 3. Now we need a bijection from S1 to S3. Well, let's see here. G goes from S1 to S2 and H goes from S2 to S3. Here's an idea. Why don't we just compose the two functions? Okay, because we know that the composition of a bijection with itself, with another bijection is also a bijection. And so we have that H compose G from, okay, and this is a function from S1 to S3, right?